Hi everyone, it's Ulysses here again for Ask Our Experts. We've gone over clock phase, so next is frequency. Along with phase and frequency, Sieg will also cover how to quantify phase error and frequency error. Sieg, what is the relationship between frequency and phase?
What I'm going to do here to answer your question is to just start with an example, because I think using an example can start to clarify what we were talking about here. And the simple example I'm going to use is two clocks. One that is running at 1.0 hertz, which is shown in red, and another clock shown in blue, which is running at 0.9 hertz. Now, the time interval between the rising edges of the 1 hertz clock is 1 second, of course. And the time interval between the rising edges of the blue 0.9 hertz clock is approximately 1.1 seconds. Now, let's look at how those rising edges change relative to each other over time. If we look at that blue 0.9 hertz clock edge, after one period, it is 0.1 seconds later than the 1 hertz clock edge. In other words, it has a phase of 0.1 seconds. If we go to the next period, we see that that red edge is now further behind the blue edge, and now this difference is 0.2 seconds. So the phase of the 0.9 hertz clock versus the 1 hertz clock is now 0.2 seconds, and so on. So we can see that the phase is changing, and that change is at a rate of 0.1 seconds per period. Another way to say this is that we have a constant rate of change. The constant rate of change is 0.1 seconds per period. Now again, as I mentioned in the previous video, we tend to prefer to express phase in terms of radians to keep things a little less confusing, so let's do that here. After one period, the phase of the blue clock versus the red clock is 0.2 pi radians. After 2 periods, that phase has increased again, and it is now 0.4 pi radians. And after 3 periods, it's 0.6 pi radians, and so on. Let's say for some reason that we expect both of these clocks to be identical 1 hertz clocks. Obviously, the 0.9 hertz clock is not ideal, and it contains errors. So we can now quantify those phase errors. And here's how we do it. Again, let's compare the rising edge of the blue clock versus the rising edge of the red clock. After one period, we see there's a phase difference of 0.2 pi radians, and this is a phase error because we are expecting it to be where the red clock edge is. Similarly, after 2 periods, the 0.9 hertz clock has a phase error of 0.4 pi, and so on. Now, if we look at the units that we use to describe frequency and phase, we get a clue of how they are related. Phase, of course, we are describing in radians, and frequency uses the units of radians per second. So I just described how we can go from phase error to frequency error in the case of a constantly changing phase. Now, we can also go the other direction. We can take a frequency error and convert that to phase error. So if we know the constant frequency offset between two clocks, we can calculate how much the phase error changes, how much it increases over time. And using the example that we've been using, we have a frequency offset of 0.2 pi radians per second. If we multiply this frequency error by the amount of time that we're measuring, capital T for example, We can then calculate the phase error at any time, capital T, and that is 0.2 pi times t. Now let's generalize this a little more, because the assumptions that I've been making here are that the phase error is changing at a constant rate, which means we have a constant frequency difference between the two clocks. In reality, a phase error may not be changing at a constant rate, and a frequency error may not be a constant, and we need a way to express this. This is where we use calculus. As we know in calculus, the derivative of a function is the rate of change, so therefore the derivative of phase is the rate of change of phase, and as we already established, the rate of change of phase is frequency. So therefore, the rate of change of phase error is the rate of change of frequency error. If we integrate a frequency error over a given amount of time, we can see how much the phase error has changed over that same given amount of time. So here's the takeaway. The derivative of phase error is frequency error. The integral of frequency error over a period of time is the phase error that has accumulated over that period of time.
Sieg, thanks for explaining clock phase, frequency, phase error, and frequency error, and how they all relate to each other. Viewers, make sure to check out our documentation on clocks and timing that we have linked in the description below. And don't forget to subscribe to our YouTube channel to be the first to know when we have more insights from our experts. We'll see you next time.